Welcome. Let me remind you that we started off this course by discussing our solar system, the planets, asteroids and various other objects that compose our solar system, after which we shifted our attention to two important tools. One is the study of fluids, fluid mechanics, and the other was the study of radiation, because much of our information in astrophysics is obtained by studying the radiation coming from astrophysical sources. We shall now move on, and the topic that we are going to take up next is stars. And we are going to start off our discussion on stars by considering the star that is nearest to us, that is the sun. So today we are going to discuss certain properties of the sun. The sun as a star, and that is the nearest star nearest to us. This shows you a picture of the sun taken on some particular day. Okay, and the information, much of our information about the sun is obtained by studying the radiation coming from the sun to the surface of the earth. Okay, and this radiation is extremely important because it is essentially the source of energy for that on the basis of which the entire life is built up on earth. So the life, for example, on earth is now sustained by eating the nutrition that is obtained from the photosynthesis, and much of our energy requirements are also met by burning fossil fuels, which were produced by converting the solar energy into other forms. So much the life on earth as we know it now is sustained by solar energy. So the radiation coming from the sun is extremely important for the survival of life on earth. Okay, so let us start off our discussion of this radiation, and this radiation is can be characterized by something that is called the solar constant. So this is the quantity that can be directly measured. So let me just draw a cartoon picture here. This is the earth and this is the sun. Obviously it is not to scale, and the radiation from the sun is incident on the earth. And what the solar constant measures is the flux of this radiation outside the earth's atmosphere, just outside the earth's atmosphere. Okay, so not all the radiation incident on the earth's atmosphere enters the atmosphere. So if you were to measure the radiation, the flux of radiation coming on the surface of the earth, it would be much less, considerably less, because part of the radiation gets reflected back. So the solar constant is the radiation incident outside on the earth's surface, measured outside the earth's atmosphere, and this has a value 1.36 into 10 to the power 3 watts per meter square. Okay, so this is the flux of solar radiation, total solar radiation incident on per unit area of the surface of the earth. Okay, and you have to measure this outside the earth's atmosphere, and it is this energy which is incident on the earth which essentially keeps us alive, keeps the whole civilization going, keeps life on earth going. So this is what is called the solar constant. Now the distance from the earth to the sun, this distance between the earth and the sun, let us call it r, is known from a variety of observations. Okay? And we have not discussed it. I leave it as an exercise for you to look up the literature and see how the value of this r, the distance, the earth sun distance, is determined. Okay? So how is this determined? Exercise. Okay, that is an exercise which you have to do. Look up the literature and find out how the distance, the earth sun distance, can be measured. Okay, and it is well known now that this has a value 1.15 into 10 to the power 11 meters. We have discussed this. This is what is called the astronomical unit, right? So, so the earth sun distance is also known, and once you know this, you can combine the flux, the measured flux, and the earth sun distance, and you can determine the luminosity of radiation coming out from the sun. So the solar luminosity L sun is the flux into 4 pi r square. Right. So this is, so these two things are directly, this is directly measurable, and this can be determined from a variety of observations. So once you know these two things, you can determine the total radiation that comes out from the sun. This is the solar luminosity. And if you do this exercise, then you will find that this has a value which is equal to that is the total solar luminosity, the total energy emitted by the sun in 1 unit second. Okay, so the sun emits 3.9 10 to the power 26 joules in 1 second. That's the wattage of the sun. It's a source of energy, just like an incandescent lamp or a bulb. It also emits out energy. Okay. Now, if you know the energy emitted by the sun, you can determine. So we know, let us try to now quantify this energy source. Okay, and when we were discussing the properties of radiation, let us assume to start with that the sun is emitting black body radiation. Okay, so let us try to make a model for the sun where the sun is a sphere. So this is a sphere. The sun is a sphere like this. This is what the sun as we see it. So let us try to make a model where the sun is a sphere of radius r sun, okay, which is emitting, it's a source, it's a black body source. Okay. Now the sun is seen to subtend an angle of 32, roughly 32 arc minutes on the sky. This can again be directly measured. You can determine the angle that the sun subtends on the sky. Okay, and so this is the angle that the sun, if you take an image of the sun, the angle that it subtends on the sky is roughly 32, around 32 arc minutes. So if you know the distance to the sun, which we already have discussed, you can, the product of these two, if you convert this to radians, will give you the radius, the diameter of the sun. Okay, so this will give you the diameter of the sun. Remember, you have to convert this into radians. Okay, this is in arc minutes. So you can easily check this for yourself. So the sun has an angular diameter of 32 arc minutes. This angle is 32 arc minutes. and you multiply it with the distance and you will get the diameter of the sun, which is twice the radius. So you can use this to determine the radius of the sun, and the radius of the sun, if you determine it, it has a value 6 point so it takes roughly 2 seconds for light to travel from the center of the sun to the radius. Okay. So we know the radius of the sun, and now we are trying to model the sun as a black body which is radiating energy. So the amount of energy that is radiated by a black body like this, we know it's the surface area 4 pi r sun square, that's the surface area, into a temperature. So if you imagine that the source is a black body and determine the temperature of that black body, then that temperature is what you call the effective temperature of the source. So we have already discussed this. So that's how the effective temperature is defined, right? So this into the effective temperature to the power 4 is the solar luminosity. So the effective temperature is the temperature that would be required by a body with the same surface area of the sun to radiate as much energy as the sun does. Okay. And so you put in the values again here. So you have to put in the values, and so the effective temperature here, if you calculate it, so the sigma, you have to put in the fact area into the temperature to the power 4 into the Stefan-Boltzmann constant sigma. So sigma, we have already calculated sigma from first principles when we were discussing the microscopic nature of black body radiation, and sigma, the Stefan-Boltzmann constant, has a value 5.67 10 to the power minus 8 in SI units. Okay, in SI units. So you have to get the units correct. Okay. So using this, if you put in these values, so we have told you what sigma is, you know what the radius of the sun is, and you know what the luminosity of the sun is. So you put in these values and you can determine the effective temperature of the sun, and the effective temperature comes out to be around 5800 Kelvin. Okay. So let me remind you what we have done. We have assumed that the sun is a black body, and using this we have estimated the temperature that the black body should have if the luminosity is to match the luminosity of the sun. Okay. Now if it really is a black body, the spectrum is then fully determined. So let us now ask the question, how well does the actual measured spectrum of the sun match that of a black body with this temperature? So how good a picture do we get about the sun if we think of it as a black body? Black body, remember, the radiation is in thermal equilibrium with matter, that's what black body is. So how good is it, how good a model, how good a picture do we have about the sun if we think of it as a black body with the temperature of 5800 Kelvin. Okay. To do this, what you have to do is you have to just compare the spectrum of the solar radiation which is incident on the earth, so you can measure the spectrum with the black body spectrum with this temperature. Okay. So this shows you the solar spectrum, and let us take a look at this picture. So this picture, this is the source from where this picture was taken, and so the maroon thing over here is the measured solar spectrum, and the gray thing over here is the is a black body curve Planck spectrum at 5777 Kelvin. Okay, 5000, close to this 5800. Okay, 5777 Kelvin, and the part of the electromagnetic spectrum that is shown here essentially corresponds to optical. This is this somewhere here is the optical part, the visual part, the one visible range, and here you have the ultraviolet part, and it extends into the infrared. And so there are a few interesting things that one should note here. The first thing that one should note is that the solar spectrum, the spectrum of the radiation from the sun, peaks in the visible part of the spectrum. Okay, so the bulk of the radiation from the sun comes in the visible part of the electromagnetic spectrum. The peak is around yellow, which is why the sun appears yellow. The sun to our eye appears yellow, the sunlight appears yellow. This is because the black body radiation and also the solar spectrum both peak in somewhere around yellow, okay, 5000, around 5000 some over there. Okay. Now, the match, as you can see, is quite good in this region. So, in the visible, the ultraviolet, and in the infrared, the solar spectrum is quite well fit by a black body at 5777 Kelvin, 5777 Kelvin. So, it is a reasonable assumption to think of the sun as a black body with the temperature around 5800 Kelvin. Okay, quite a reasonable assumption, because you see that the black body curve gives a reasonably good fit to the solar spectrum. Okay. Now, and the bulk of the radiation actually comes in this visible ultraviolet and infrared part. So, the bulk of the radiation coming from the sun can be well modeled using a Planck distribution, a Planck distribution spectrum, or using a Planck spectrum. But if you look at other wavelengths beyond this range, so if you look at wavelengths beyond this range, which have not been shown here. So, if you go to shorter wavelengths, you have the far ultraviolet, and you have X-rays, and then you have gamma rays. The fit there is the observed spectrum there is not well fit by black body spectrum at 5800 Kelvin. So, let me show you a few pictures before we discuss it. So, this is an X-ray picture of the sun. This picture has been taken by the Yoko Soft X-ray telescope, and this is an X-ray picture of the sun, and the X-ray radiation coming from this would if you compare it with the black body spectrum, it would correspond to something like 1,000,000 Kelvin, which is quite different from the temperature which characterizes the bulk of the radiation, which is at 5800 Kelvin. Okay. So, the X-ray radiation, actual X-ray radiation from the sun is far in excess of what you would expect from a black body spectrum with this temperature. Okay. So, it is far in excess of what you would expect from a black body spectrum of this temperature. The X-ray, also far ultraviolet. This is a ultraviolet image of the sun taken. This image is from the Soho observatory. This is a space observatory, and this image over here measures the ultraviolet from highly charged iron ions. Okay, and the bright parts in this image would tell you that the temperature there is around 1,000,000 Kelvin, which again is far in excess of 5800.
So, the temperature is determined by assuming
Yeah, in the previous thing. Okay, and here it is from iron. So you can ionized iron. So you can determine the conditions required to ionize and produce that much radiation from iron. No, no, no. It's not. It's at a particular spectral line, right? For iron, yeah. Okay. So if you infer a temperature from this, the temperature of the medium there would be around 1 million Kelvin. Okay, it's a particular line. So it's a particular line which is emitted by highly charged, highly ionized iron. Okay. So well, there are methods of doing it. Okay. Uh, so the main point is that if you go to wavelengths which are beyond the ultraviolet, far ultraviolet, X-ray or even gamma rays, you find that the radiation is far in excess of what you would expect from a black body curve. But if you look at the contribution to the bulk of the radiation, that is very small from those regions. The bulk of the radiation is over here, and that is well characterized by a black body spectrum. Okay. Similarly, if you look at the radio part of the spectrum, that is the larger wavelengths, there again you have radiation in excess of what you expect from a black body curve of if you extrapolate this black body curve, and all of these things are associated. So the amount of radiation in these ultraviolet X-ray or in the radio, they are closely linked with activity on the sun. The sun is not a peaceful spherical object emitting radiation continuously. There is all kind of activity on the surface of the earth. You can see some of it in this picture. So you can see that there is some material being ejected over here. This is a solar flare. So there are bursts and flares, and the radiation, for example, in radio or in other wavelengths, it goes up when you have these flare activity increasing. Okay, so that is a function of time also, and you can even observe gamma rays related with these solar flares and bursts. Okay, so the other parts of the spectrum, they are not well described by this particular black body. That is the first thing. Now, even in the bulk of the spectrum, so we have seen that around 4000 Armstrong, it is quite well described by a black body spectrum. But if you take a closer look, so this is a high resolution spectrum. Okay, so let us see how high resolution it is. So this, from here to here, this entire thing is 20 Armstrong. Okay, and from here to here again is 20 and 20 and then like that. Okay, so it's a very high resolution spectrum. This entire range over here corresponds to 20 Armstrong. Okay, and if you look at it in a high resolution, if you look at high resolution, then you see that on top of this continuum, so you have this continuum radiation. Okay, this is what is the continuum radiation. It's continuous. It's not a discrete function. There are no discrete ups and downs. And on top of this continuum, if you look at it very closely, you will find these absorption lines. Okay, you can find these absorption lines, and these absorption lines correspond to different transitions of atoms. So here you have Balmer H gamma line. You could have different kinds of such lines. Okay, so if you take a close look at the spectrum at a very high resolution, you find that on top of the continuum spectra, so what we mean by this, let me show it schematically. So if you look at it at very high resolution, or you could draw it as a function of frequency, then this is the continuum that you have. On top of this, you have these absorption lines. So actually the spectrum falls here, and then it goes down here, and there are absorption lines like this. Okay, so there are all kinds of such absorption lines which you can see on this in these pictures. Okay, and these are often referred to as the Fraunhofer lines, or the whole thing is referred to as Fraunhofer spectrum. Okay, so this is what you see if you look at the solar spectrum in detail at high resolution. At low resolution, it is quite well fitted by a black body spectrum. Okay, there is another evidence. Let me show you that, and then we shall discuss the implications. And this evidence is limb darkening. So this shows you a picture of the sun, an optical picture of the sun. And if you look at this picture, I am sure you can make out that it appears brighter in the center, and it appears to get darker as you go away from the center towards the edges. And in astronomical parlance, the edges are referred to as limbs, and this is the phenomena shown over here is referred to as limb darkening. So the outer regions get darkened. So the outer regions of the sun appear to be darker. Okay. Now, if the sun were a black body of the same temperature, then it should appear equally bright, because the temperature is the same everywhere, right. So this is something that seems to indicate that it is not exactly a perfect black body. There are some deviations from that. These spectral lines, now, so there are atoms. So these spectral lines, what do they tell us? So from these, looking at these spectral lines, we can see that there is material in the sun which is cooler than the rest of the material, right? Because if the entire material were at the same temperature, then it would be all in thermal equilibrium, and you would just get the Planck spectrum. Okay, so it indicates that there is material in the sun which is cooler than the rest of the material, and if you have cooler material, it will then absorb. So there are temperature differences that you are seeing essentially. Okay. Now, so there are temperature differences on the sun, and the thing is that we would like to understand these. So the question arises, does the temperature increase or decrease as you go into the sun? So let me draw a picture. So the question is, this is the sun, and if we go into the sun, does the temperature increase or decrease? That is the question that one could ask. Now we know that energy flows out from the sun, right? That is a well-known fact. So we know that energy flows out, radiation flows out, and we also know the laws of thermodynamics, that heat flows from hotter to cooler regions. So this would tell us clearly that it is hotter inside and it is cooler as you go out. Okay. Now okay, so that is the broad picture. It is not that the whole thing is precisely one black body with radiation and matter in thermal equilibrium at the same temperature. There are temperature gradients, we believe, and it is hotter inside the sun, it is cooler outside. Okay. So let us use this picture to make some idea about the sun. Okay. So the first thing that we would like to discuss is the phenomena of limb darkening. Okay. So let us first take up for discussion the phenomena of limb darkening. And we shall make a very simple model for this, which may not give you the entire picture, but it will give you some idea of how one could go about modeling and understanding what is going on. Okay. So the sun is spherical, so we shall not go into this spherical geometry, we shall make a very simple model. Our simple model is that we are looking at some plane parallel kind of a thing. So we shall assume it to be plane, okay, and the temperature, so this is on the right hand side we have the sun, so this is the sun, the material of the sun, and we shall assume that the temperature at the surface is T naught, and the temperature increases as we go inside, okay, it increases with distance inside the sun. Now we have, remember that when we discussed the propagation of radiation, I told you that it is most convenient and natural to quantify length intervals using the optical depth, right. Optical depth was alpha, the absorption coefficient into distance x, alpha into x. So the distance inside we are going to quantify using the optical depth tau, that is the important thing for radiation, right. So we shall assume that the radiation inside this increases and it is T0 plus A into tau. So we will assume that it increases linearly inside. That is the simple model that we shall make, okay. So the optical depth is 0 over here, and as you go inside the optical depth increases, and let us say that it increases all the way to infinity or to a very large number as you go inside the sun, okay. So let us, and this entire thing is thermal medium, so each part over here is a thermal emitter, okay, and at a temperature T which is given by this. This is our model for the sun, okay. We shall forget about the fact that it is spherical, plane parallel, okay. So let us now ask the question, we are looking from this direction, the observer is here and the observer is looking into the sun, okay. So actually it is the radiation from the sun coming to the observer. So let us ask the question, what is the radiation received by the observer from different directions on the sun? So we will call this angle theta. Okay, and this is how it increases with optical depth if we go straight inside the sun. Now if you go with optical, instead of going straight in, if you look at a light coming from this direction, what would be the temperature as a function of the optical depth? So optical depth is alpha into the distance, but the temperature will increase only by this amount. So for any angle theta, the temperature is going, this is going to be multiplied by factor of cos theta. So there will be a factor of cos theta here if I am looking at some other angle, right. This is if I go straight in, but if I go at an angle, the optical depth is going to increase, but I am not going to go the same distance inside the material. So the temperature increases like this, and I am now going at an angle, so the temperature increase is not going to be as much, it will be less. Now let me write down the general solution. We have already solved the radiative transfer equation, so we can straight away now write down the general solution in terms of the source function inside this material, okay. So let me write down the general solution, and the source function inside this material is just the Planck spectrum. So the source function inside this material is the Planck spectrum at the temperature T. So the material inside this is emitting thermally at a temperature T, where T is increasing as we go in. The temperature increases as we go in. That is the main thing. Okay, so the source function also increases like this. So we can straight away write down the solution, and the solution we know is I nu at this point, the solution is equal to, so what is the solution? We have to take the contribution from each element over here, and the radiation from here when it propagates to here will be attenuated by a factor e to the power minus tau. That is the main thing, and you have to add up the contribution from all such elements as you go in. Okay, so this is going to be 0 to infinity, and then you have the source function, which here is b, the Planck function, which is a function of the temperature at that optical depth, into e to the power minus tau d tau. Right, this is the solution. So this is the specific intensity that is going to be measured over here. So each small interval d tau is going to emit this much, that is the source function, and it is going to get attenuated by a factor e to the power minus tau inside, and I have to add up the contribution from all the way inside. Okay. So this is the specific intensity over here in this situation. Now we will simplify the problem to some extent. So what we will do is, we will assume that this is, we can describe it in the Rayleigh-Jeans approximation. In the Rayleigh-Jeans limit, so in the Rayleigh-Jeans approximation, we can write this as 2 Boltzmann constant by lambda square into a temperature. Right, the relation between the source function and the temperature is quite simple, it is a linear relation. So we will assume that we are working in this limit, and the specific intensity then also is 2 kb by lambda square into the brightness temperature which you would measure. So we are quantifying the intensity in terms of a temperature, the brightness temperature, and in the Rayleigh-Jeans limit they are related like this. So the more the brightness temperature, the more the specific intensity or brightness. Okay, so we can now write down this equation straight away in terms of the temperatures. Just get rid of the factor of 2, the Boltzmann constant by lambda square, and we have that the brightness temperature over there is equal to 0 to infinity T0 plus a tau, that is the temperature of the source at the corresponding point, e to the power minus tau d tau. Okay, so we have to do these integrals, and both of these integrals we can easily check, they give you a value 1 right here. So you have to integrate e to the power minus tau d tau from 0 to infinity, and this has a value 1, right. So and also equal to 0 to infinity tau e to the power minus tau d tau. Okay, both of these integrals have value 1. So it tells us that there should be a factor of cos theta here. The relation between temperature and optical depth is different in different directions, cos theta. Okay, so what it tells us is that the brightness temperature T is a function of cos theta, and it is equal to T naught plus A into cos theta. Okay. So we have worked out the brightness temperature profile that the observer over here would see if he were to look into the sun under these assumptions. So the assumption is that the temperature inside the sun falls off linearly as you go inside, and the whole thing is plane, and we have assumed, we have worked in the Rayleigh-Jeans approximation. You can do the whole exercise more rigorously, putting in the spherical geometry of the sun and working in the entire with the correct Planck formula, but our aim here is just to get a qualitative idea, a rough quantitative and qualitative idea of what is going on. Okay. So what are the messages that we can derive from this simple exercise? Let me enumerate them one by one. So the first message is, so this is the, let me draw a picture again. So this is my medium I am observing here, and this is the angle theta, and the temperature inside is has a gradient like this. It is increasing linearly. Okay. So what do we see? The first thing that we see is that the brightness temperature that will be observed is actually the temperature where the optical depth becomes equal to unity. Okay. So the brightness temperature corresponds to the temperature at the place where the optical depth becomes unity. Okay. So the temperature inside is T0 plus A tau cos theta. As you go inside the medium, the optical depth increases, and the temperature of the radiation that you will see here is essentially the temperature at the place where the optical depth becomes becomes unity. Okay. So when you observe the radiation from the sun, we are observing the radiation essentially from the part of the sun's atmosphere where the optical depth is of the order unity, is 1. Okay. If you go inside the sun where the optical depth is larger, so photons that are emitted over here, what happens to these photons? The optical depth here is large. So the probability of a photon propagating is e to the power minus tau. So the photon that is emitted here gets absorbed by the time it comes to the surface. Okay, so the photons that are emitted at high optical depths get absorbed inside the medium, so they don't come straight to you. The temperature here is higher, but these photons that are emitted inside do not propagate to you, they get reabsorbed inside, and it is only the photons that are emitted around the region where the optical depth is 1 which can propagate freely more or less to you. Okay, so when you are looking at a medium that has got temperature gradients and things like this, you will see the radiation from the region where the optical depth is of order unity, and you will be seeing the region which is, so this is where, let us say, the optical depth becomes unity, and the region is not going to be the, okay, so let us say this is the point, then you will see the radiation coming from this entire part where optical depth is less than or up to order unity. This region is called the photosphere. That is the part of the sun which you see from outside. It is called the photosphere. So all the way till where the optical depth becomes of order unity. The second point is that the temperature of the radiation, if you plot it as a function of theta, when you look straight into the sun, the temperature will have a value T naught plus A. When you look at a grazing angle it will fall. So the temperature profile, this is pi by 2, the temperature profile will look something like this. Okay, that is just cos theta basically, T naught plus cos A. So as theta increases, the value of cos theta falls and the temperature is going to fall. So if you look in this direction, you are going to see a smaller temperature as compared to this direction. And why is that so? That is so because optical depth 1 is reached at a much shallower place, whereas here you are going straight in, so optical depth 1 is reached much deeper. And since the temperature increases inside, so if you look straight in, you are looking at a much hotter part. If you look at an angle, you are looking at a cooler part. Okay, I hope that picture is clear. So when you look at an angle over here, optical depth 1 will possibly be reached over here, whereas in this direction it will be reached much deeper inside. So when you look at an angle, you are looking at a shallower part of the sun where it is also cooler. Okay, and as a consequence, the temperature here is also of the radiation coming from here is also going to be less. So this, so when you look at the sun, so let us look at this picture of the sun. When we look at the sun, when we make an image of the sun, when we look straight in, we are looking deeper into the sun and it appears hotter. The sun is hotter as you go in. When you look straight in, you are looking deeper, so you are seeing a hotter part of the sun. If you look at an angle, the optical depth becomes 1 with at a much shallower place, so the temperature there is less as compared to what you would have probed here, so it appears darker. The brightness is less. Okay, the temperature is less, so the specific intensity is also less. Okay, so this is essentially direct evidence, limb darkening, that the sun is actually hotter as you go in. Okay. Now let us also look at the second thing. So let us try to now model what causes those spectral lines, cooler lines that you see. Let us try to make a model for that. Let us try to get a brief understanding of what is going on over there. So to do this, let us make a model. So when you look at the sun, we have seen that you only see the region where the optical depth is of order unity. So let us think of the sun as an opaque sphere of some temperature Tc. This is the core, and this is where the optical depth is of order unity. Looks like this. You do not see inside this, so it is opaque. Okay, so we have an opaque sphere of some temperature Tc, and let us now consider an atmosphere. This is the atmosphere of the sun, the thing outside it, a shell of gas at a temperature Ts, and Ts we have seen will be less than Tc. Okay, so this is our model. The atmosphere, the outer shell of the sun, where the optical depth is less than 1, is at a lower temperature Ts. As you propagate inside, the optical depth increases, and when it becomes 1, we think of it as an opaque sphere inside it at a higher temperature Tc. And let us assume that this shell is filled with a gas which has two energy levels, and the transition between these two corresponds to a frequency nu naught. Okay, and in our discussion of the of these two level transitions, I have told you that there is this line profile phi nu. It really doesn't, the transition really does not occur at a single frequency, it will occur in a spread of frequencies. So let us model this by the line profile phi nu, which looks something like this. Okay, so let us now, so the absorption coefficient alpha is large when you are near nu naught, right, for this material outside. But if you are away from nu naught over here, the absorption coefficient is extremely small, and the optical depth is proportional to the absorption coefficient. So the, if you are at a frequency over here, somewhere over here, the optical depth is more than 1. If you are at a frequency over here, the optical depth is much less than 1. Right, this material does not absorb anything over here. That is the model. That is the gas which fills the outer shell. It has two states, and if you are at a frequency which corresponds to this difference somewhere near here, then the absorption coefficient shoots up, and this response is described by this line profile. Okay, so let us now consider a line of sight which goes like this, through this. Okay, and let us look, so in general we can write down the solution, we have already worked out this. So if you have something like this, so the solution, the specific intensity outside, we can write down straight away, the specific intensity outside is going to be the specific intensity of this radiation, which is B nu tau c attenuated by this optical depth, right, plus the Planck function of the shell outside. These are all thermal, the material here is in thermal equilibrium at Ts, the material here is in equilibrium at Tc, so they are all emitting, the source function and the intensity are all Planck spectrum. This into 1 minus e to the power minus tau, right, this we have already worked out. So this is the background specific intensity, it gets attenuated by this factor, this is my source, and the contribution from this source, if it is at a uniform temperature, is 1 minus e to the power minus tau. Okay, so what happens when you are looking far away over here? So when you are looking where in the region where the optical depth is much less than 1, in that region I nu, the specific intensity, is essentially B nu Tc. So this, if I do a Taylor expansion of this now, this will become 1 minus tau, and this will become just tau. So I have plus into tau, right. So if my optical, it's optically thin, this is a negative number, so there will be a small decrement, and as the tau tends to 0, this small decrement will be gone. So I will essentially see the black body spectrum of this. Now let us consider the other limit where the optical depth is greater than 1. So where the optical depth is greater than 1, in the limit in the limit where the optical depth is extremely large, let us just look at that limit. So if the optical depth is much greater than 1, then I nu will go over to the temperature, black body spectrum with temperature of the shell. Okay, and if you have the intermediate region, it will slowly go from this value to this value. As you approach this frequency, the specific intensity will slowly go from this value, tau is very small, so I have this. As you approach larger and larger tau, it will slowly go over to this value, and then again it will come back to this value. Okay, so let me draw a schematic diagram of what you expect. So if the shell were not present, then I would have something like this continuum black body spectrum, but because of this, so this is at a temperature T core, but because of the material in the shell which is at a temperature which is lower, near nu naught the specific intensity will go down and it will approach the value Ts, the black body spectrum corresponding to Ts. Here it will be a black body spectrum corresponding to the core temperature. Near nu naught, if the optical depth is extremely large, it will approach a black body spectrum with temperature of the shell. Okay, so it will appear, they will be less brighter, and this is how we can understand these absorption lines that you see in the spectrum. So so in the atmosphere of the sun, the outer parts are cooler, and you have these two atoms over there which have got two level transitions which cause these absorptions that you see. Okay, so in today's class we have discussed our picture of the sun and other stars in general, so all other stars in general. So what we see is that the overall spectrum near the peak is well described by a black body. Away from the peak, the black body doesn't give a good picture, and the atmosphere, you can think of it as the temperature increasing as you go inwards. The part of the star or the sun that we probe is where that we probe through our visual electromagnetic observations is the region till where the optical depth becomes of order unity. Okay, and the temperature increases as you go inside the star. So let us stop our discussion of the sun and stars here for today. We shall resume on this in the next class.